Hello everyone, I'm Norman Wildberger, and we're talking about the sociology of pure mathematics. Today I want to talk about arithmetic, a fundamental subject in mathematics that actually leads to a lot of potential controversy and logical difficulty and actual social interaction in terms of moving the subject forward. Obviously, arithmetic has been part of the mathematical story since early days, since ancient times. And I want to start there, or at least with the first two great civilizations, the Egyptians and the Mesopotamians. And we're going to talk about their number systems, and both of them are really interesting. Today we're going to concentrate on the Egyptians, and in my next video I'll talk about the Babylonians and the Sumerians. But just to give you an overview, okay, these two number systems are quite different, although they share a few aspects. But the differences between these two number systems, in some sense, is reflected even in the modern story. Okay, so the Egyptians, well, we're talking about the Egyptian civilization of 3000 BC to roughly 0 BC when the Romans took over. Almost a continuous, fabulous culture that has fascinated mankind for thousands of years. While on the other hand, the Mesopotamians, relatively unknown until the 19th century. And now we realize there was a civilization there which was every bit as interesting and rich, perhaps, as the Egyptians, but they didn't leave so many vast stone, pyramids, tombs, temples, and so on, like the Egyptians did. But they, in fact, left us a lot of clay tablets. So from some point of view, we actually understand the early Sumerian, Babylonian culture in maybe deeper ways than we do with the Egyptian one, in the sense that we have a much broader written record. Okay, arithmetically, the Egyptian system is perhaps more familiar because it's based on base 10. So they have a basic symbol for 1, a vertical stroke, like most cultures do. And then there's an upside down U for a 10, a curly C for 100, and then 1,000 is represented by some kind of flower. And they have some other symbols representing further powers of 10, like fingers and toads and who knows what. Okay, so for example, the number 1,237 in our Hindu-Arabic decimal system would be represented by them like this. There's a 1,000, there's 2 hundreds, 3 tens, and 7 ones. Okay, so that's what we're going to be talking about today, the arithmetic built up from this, this notation. I do also want to mention, just though in contrast, the Babylonians, they were around 2000 to 1600 BC, took over from the earlier Sumerians and Akkadians. They had remarkably a sexagesimal or base 60 system, which I talked about in some other, some ancient mathematics series on Babylonian mathematics. So this is very interesting. They had ones represented by vertical strokes made typically on a clay tablet with a stylus. And then the other symbol they had was sort of a wedge opening to the right, which was a 10. And using just these two symbols, they were able to construct digits from 1 to 59. So this would be 35, 3 tens, and 5 ones. And then they would put these digits together in a manner that's very parallel to our Hindu-Arabic system. So instead of having ones, tens, hundreds, and so on, they would have ones, 60s, 60 squares, etc. So this number that we see here, well, there's a 24 on this digit, and here there's a 49, okay? That would be represented by them as 49 ones, like there are 7 ones here, and 24 60s, just like there are 3 tens up there. So for a total of 24 times 60 plus 49, 1489 in our system. But it's important to note that they had a different view of sort of place value. They were more flexible as to the scaling of their number system. So the symbol for 60 that they had was, at least in the Babylonian times, pretty well identical with the symbol for 1. So 1 and 60 were basically the same to them. So this could also be interpreted actually in a multiple of ways. And also they also had the same symbol for 1 over 60. So they had a kind of a decimal system where you're allowed to describe numbers less than 1 also with exactly the same system. So we'll talk more about that later, but I just want to alert you now that roughly speaking, the Egyptians had a system that's more oriented towards fractions when it comes to subdividing things, while the Babylonians were more like a base 60 analog of our decimal notation, where you use digits like this, a decimal point, and then further digits to the right of the decimal. They didn't have a decimal point, but they still had an effective arithmetic that was basically equivalent to that. So the story today, the Egyptians and their remarkable approach to fractions, which sheds a lot of light on the way we think about our arithmetic and what we teach young people at schools. Now, while the Egyptian civilization is surely the most remarkable in terms of the richness of the artifacts and the tombs and the pyramids and so on that they left behind, in terms of actual written material to try to understand, say, their mathematics, we don't have actually so much material, unfortunately. Contrast that to the Mesopotamian situation, where we have a distinct lack of monumental buildings. Most everything is built in clay and it's now ruined. But we have actually huge numbers of tablets because the clay tablets often survived when the buildings didn't. So it's interesting, we have the very different ways of trying to understand these two cultures. Okay, in terms of Egyptian records, written records, we don't have a lot, and notably we have something called the Lahun papyrus dating from roughly 1800 BCE, the Moscow papyrus dating from 1700 BCE, and the Rhind papyrus. This is the most well-known, and it's the biggest and has the most information, so it's really the most important. And it was written by a scribe. We know his name was Ahmes, and it was written about 1550 BCE, but it's very likely a copy, or at least a partial copy, of earlier things. Okay, so we can learn a lot from these manuscripts, even though we don't have so much information from them. And a notable first thing is to appreciate how they did multiplication. They actually implicitly used sort of a binary approach to arithmetic. So thousands of years before binary arithmetic sort of was officially studied in the European time by Leibniz. So let's say you wanted to multiply 12 times 37. Okay, so what they would do is they'd say, okay, let's start with 12 and let's double it. So doubling something or having something, these were sort of important, sort of easy operations. Okay, so you could relatively easily double 12 to get 24. And of course, I'm writing everything in the Hindu Arabic form. Of course, they would write things with their strokes and their upside down horseshoes and and their curly C's, etc. So we have 12. 2 times that is 24. 2 times that is 48. That's 4 times 12 altogether. Then 8 times 12 is 96. And 16 times 12 is 192. And 32 times 12 is 384. So each of these is just obtained from the previous by doubling. So we double, and then we have this row. Okay, so now let's say we are interested in 12 times 37. Okay, so what we want to do is we want to think about this as 12 times in sort of modern notation. We want to decompose the 37 as a combination of these powers of 2. Okay, so we could take this one here, this 32, and if we add 4 to that, then we get 36. And we add 1 more, then we get 37. Right? So we can write 37 as 1 plus 4 plus 32. Okay, and so then we can use the distributive law, saying, okay, so that this product is going to be the sum of 1 times 12 is 12, and 4 times 12 we can read off is 48, and 32 times 12 is 384. And now we do some ordinary arithmetic. I guess 12 plus 48 is 60. If we add 60 to 384, we're going to get 444, I suppose. So that's how they did their multiplication. So the real test of an arithmetic is how do you deal with the difficult operation, which is division. And correspondingly, how do you deal with quantities which are not integral copies of 1. In other words, smaller quantities other than 1. So the Egyptians had a theory of fractions, and it's sort of parallel in some ways to what primary school students today would learn, but there are very important and interesting differences. And my exposition of this draws a lot upon this nice article by A.S. Daiff called Mathematics in Ancient Egypt from 2650 BC to 50 BC. So first of all, they had a notation where they had a kind of an I. This is supposed to be an I, and underneath it there would be a number, and then this would represent the fraction that we would write as 1 over 3. So if you put a horseshoe here instead, then you get 1 over 10, and so on. Notably, there's not in this notation the ability to change the numerator, right? So you have some place where you can change the denominator, but you can't change the numerator. It's always 1. And that's a crucial property of their arithmetic, and this is sometimes referred to as the Egyptian fractions. Okay? When people talk about Egyptian fractions, they're talking about expressing a number with combinations of these particular kinds of fractions. 1 over 2, 1 over 3, 1 over 4, 1 over 5, etc. Now, they actually did have a few special symbols for a few different ones, like 2/3. Okay, 2/3 is often a little bit special. 3/4 also has a special notation. But generally speaking, their fractions were of this kind. And to create more general kind of quantities, they would just add these things, but without repetition. So they would aim to not repeat anything. Okay, so they did not use our notion of fractions with numerators and denominators like 5 over 7. And this is a pretty interesting question that we can ask. Well, why not? Is it because they were unsophisticated? Because they didn't think hard enough about it? Or is there actually a good reason for their system? And does it shed light and maybe even shed some questions about our arithmetic that we teach our young people? So I have to say a little bit about our arithmetic. And I know you're potentially a social scientist. Maybe you did not like mathematics in school, and maybe you're one of the many people who get sort of turned off or disoriented with the theory of fractions when it's taught in primary school. It is a difficult thing, and we should appreciate perhaps why it's a little bit difficult, okay? That our use of fractions makes division, okay, which is this difficult operation, in some sense trivial. Okay, so that's sort of an initial reason. For example, when you divide 24 by 6, then you look up something on your multiplication table, or perhaps you remember that 4 times 6 is 24, and so that allows you to undo that multiplication to deduce that 24 divided by 6 is equal to 4. That's fine. But what happens if you want to, say, divide 24 by 7? Well, we know perhaps that, or you can remember in the multiplication table, that there's no multiple of 7 that equals 24. Okay? 7 times 3 is 21. 7 times 4 is 28. So it misses 24. So it doesn't go evenly. But the fraction story allows us to write an answer to this. And we say, okay, that the result of this division is 24 over 7. Okay, this is then a new kind of number, and you can see that one of its roles is to somehow circumvent the need for actually doing division. Okay, it's an interesting point, and it's one that a Babylonian scribe would definitely think this, because they would think of this as highly suspect. So what this implies, however, is that questions can have multiple answers. So let's say, for example, that we have this more complicated problem, okay? 663 divided by 39. So if we apply the same reasoning, well, we could just write down 663 over 39. But then there's this sort of nagging suspicion, well, is that the best we can do, or can we, sort of simplify such a fraction? Because in the world of fractions, there's multiple ways of writing or representing the same fraction. So in fact, if you know a little bit about numbers and divisibility, you see that the sum of the digits up here is 15, which is a multiple of 3. That means that this number is divisible by 3. And the sum of the digits here is also divisible by 3. So both top and bottom are divisible by 3. So if we divide out by 3, top and bottom, divide this one by 3, we would get 2, 2, 1. And we divide 39 by 3, we would get 13. So now that's an alternate answer to the question. Maybe it's arguably a better answer, but in fact, it's still not the simplest answer, because you may not immediately remember this, but it turns out that 221 is actually a multiple of 13. It's actually, this thing here is actually 13 times 17. So we can actually divide a factor of 13 out of all of this. So we do that, divide top and bottom by 13, we get 17 over 1. And then it's usual to represent that as no longer a fraction exactly, but just as a regular number, 17. So you see that there is sort of multiple possible answers to questions, which is admittedly a complication with our theory. Another aspect of our arithmetic, which is very noticeable if you do a lot of calculations. So I have a theory of trigonometry called rational trigonometry, and I make lots of calculations with fractions. And what you find there is that very quickly the results of calculations get big, because our rules for adding and subtracting and multiplying, dividing fractions make them grow. The numerators and the denominators get big relatively quickly. Okay, so that's a little bit of a complication, because once you have a big fraction, like with a big numerator and a big denominator, it becomes hard to assess just how big this thing is, compared to, say, the regular numbers like 17 or 18 or something. It's hard to see clearly what kind of a quantity this really represents. So this is a complication with our theory of fractions, even though it does have some benefits. For example, it makes division quite simple. Okay, now at the risk of annoying thousands of educators, I'm going to share with you a kind of a trade secret, okay, about fractional arithmetic. Arguably, the strongest reason for teaching young people fraction arithmetic is not so that they can actually do fraction arithmetic. Okay? It's really to prepare them for algebra. Let me illustrate that with this example. So I hope you'll indulge me just in a little bit of review of primary school addition of fractions. Okay? So here are two fractions, 2 over 3 and 4 over 7. We want to add them. I remind you, this is what you were taught in primary school, although you may have forgotten it. What you do is you have to get everything over a common denominator. So you multiply top and bottom here by 7. So you get 2 times 7 over 3 times 7. And you multiply top and bottom over here by 3 to get 4 times 3 over 7 times 3. And the reason you've done that is that now the denominators are the same. They're both equal to 21. So this fraction here is now same as 14 over 21, and this one here is 12 over 21. And once the denominators are the same, then you can just add the numerators, and 14 plus 12 is 26, so the answer is 26 over 21. That's how you add fractions. Now, when you go to algebra and you're dealing with variables, in the world of polynomials, then you are often in a position of having to do something very similar. So you may have to add a over b plus c over d. And now we're not working in the world of fractions or numbers anymore. We're working in algebra, which is more sophisticated. But crucially, the same thinking applies. So what you have to do to simplify this is you multiply top and bottom here by d. So you get a times d over b times d. And you multiply top and bottom here by b. You get c times b over d times b, and now the two denominators are the same. They're just b times d. And so then you can add the numerators, so you get ad plus bc. So if you have not learned how to add fractions, then when you get to algebra, like at first year university, then it's a hurdle for students. Okay, so now there's a legitimate question that the public might ask here is, okay, that's very well if our students are aiming to do advanced courses in algebra. What if they just want to be regular people? Is it really justifiable to spend as much time learning fractions as they currently do? And I think this is a legitimate question. Maybe I won't give an answer to it, but I think it's a legitimate question. And we should be cognizant of the fact that even in the early part of the modern era, Simon Stevin, who was a Flemish mathematician and inventor, he strongly advocated that in practical terms, to do ordinary life, you didn't want to use fractions. Okay? What you wanted to do was to replace fractions with the decimal arithmetic coming from the Hindu-Arabic system. You want to convert everything to decimals and do it in the world of decimals. And his argument was very convincing, and since then, more or less, scientists and engineers have adopted exactly this position. Okay? So fraction arithmetic is not something that you're going to find in science generally, and it's not something you're going to find in engineering generally. There might be some special cases. And sure, you need fractions if you're doing elementary cooking, dealing with half a cup of this or 3/4 of a tablespoon of that or something like that. But those are pretty elementary kinds of examples. More complicated fractional arithmetic, it's really questionable whether it's valuable for actual practical applications. And an Egyptian scribe would agree exactly with what I'm saying. And they might say, yes, but that's because your fraction system is not as good as our fraction system. So let me illustrate for you the actual potential case for the superiority of the Egyptian point of view to our point of view. Okay, so from a certain point of view, their system makes more sense than our system. And I'm going to share this with you in terms of this very specific example. Suppose you had 5 loaves of bread and you had to split or divide that equally amongst 7 workers. So this is a kind of problem that the Egyptians probably faced in a big scale because they had these huge construction projects involving tens of thousands of people, and there had to be camps and communal kitchens and so on, work groups, and so things would have to be divided. So you've got 5 loaves of bread and you have 7 people. How are you going to divide them up? Well, our modern answer is, well, divide 5 by 7, you get 5/7. Okay, so what actually are you going to do? Well, you're pretty well obliged to take each of these loaves and divide them up into 7, okay? And so I've divided each of these 5 loaves into 7, 1, 2, 3, 4, 5, 6, 7. And then each worker gets 5 of them. So first worker, 1, 2, 3, 4, 5. There's your 5/7. The next worker, 1, 2, 3, 4, 5. There's your allocation. And so on. So now let's switch to the ancient Egyptian point of view. The scribe Ahmes's answer to the same question would be, every worker gets 1/2 plus 1/7 plus 1/14 loaves. So this is an Egyptian fraction. All the fractions involved here have numerators of 1. And it's not too hard to see that this total is the same as 5/7, because if we get a common denominator, the common denominator would be 14. Okay, so that's 7 14s, that's 2 14s, that's 1 14, so 9 plus 1, 8 plus 1 is 9, plus 1 is 10. So 10/14, which is the same, divided by 2, same as 5/7. Okay, what's the advantage in thinking about it this way? Well, what you need to do with your 5 loaves is you need to cut these 3 into equal pieces, just divide them by 2. This one you're going to divide into 7, and this one here you're going to divide it in half, and then half of it you're going to divide into 7 pieces. So, worker number 1, well, you get 1/2 a piece, there's your 1/2 a piece. You're also going to get 1/7 of a piece, there's your 1/7, and you're going to get a 14th. That's that one there. Okay, then the next guy. There's your 1/2, there's your 7th, and there's your 14th. And so we just carry on like this. There's altogether 7 halves if you include that one. So there's 1 for each worker. There's 7 of these 1/7 pieces. They're all arranged there. And there's 7 of these 1/14 pieces all arranged there. So everyone gets the right amount. And it's much easier subdivision than this one. And moreover, you can sort of see more clearly how big this number really is. Because this first term, they always write the biggest fraction first. Gives you kind of the first approximation to this number. Okay, it's a little bit bigger than a half. And then you throw in the next one. Well, that teaches you a little bit more. So it's a half plus a seventh. Now you have a pretty good idea. And then there's this final thing that's a little bit of extra information. Then you have the thing entirely. But it sort of shares a little bit of the aspects of the decimal number arithmetic that as you read from left to right, you're kind of getting more and more refined information. You're getting the most important information at the beginning, and then more refined information as you carry on. Yes, you ask, but okay, how do they do arithmetic with these fractions? How do you add fractions? How do you multiply such fractions? Okay, so that's an interesting question, and it turns out that they had a pretty significant tool to help them do this arithmetic. And that was a particular table. And this table is very clearly laid out in the Rhind Papyrus by Ames. And in fact, it also appears in one of the earlier papyri, the Lahun papyri. So what this is a table for 2 over n, where n is an odd number going from 3, 5, 7, all the way up to 101. Okay, so this is representing how we would, they didn't use this language, but how we would represent 2 over some odd number. So for example, 2/3, okay, here are the values, 3, 5, 7, down to 27, down to 49, and 51 to 73. And I'm going to show you the rest after the next slide. So this thing here means that 2 over 3 can be written as, in terms of unit fractions, there's a 2 and a 6. That means we have to use 1/2 plus 1/6. Okay, 1 over 2 plus 1 over 6. So that's how you write 2 over 3. 2 over 5 is 1 over 3 plus 1 over 15. 2 over 11 is 1 over 6 plus 1 over 66. 2 over 13 is 1 over 8 plus 1 over 52 plus 1 over 104. So there's 3 constituents in that case. And some of them have 4 constituents, like this one here. So 2 over 43 is 1 over 42 plus 1 over 86 plus 1 over 129 plus 1 over 301. Now, this table and its completion, there's a few more rows I'll show you, is really a remarkable thing. Okay, so this is 1550 BC, but the 1700 BC, maybe 1800 BC table has something similar. Okay, so this is clearly a major and important kind of computational device that the Egyptians developed to allow them to do their arithmetic. And it turns out that it's really quite a remarkable piece of mathematics, because it turns out that Ame's choices here are quite efficient. So it turns out that there's not a unique way of doing this. Right? There are many potential ways of writing one of these reciprocal things like 2 over 63 in terms of Egyptian type fractions. But somehow or another, Ame's table picks out the best ones. And best in what sense? Best in the sense that the number of unit fractions required is minimal, first of all, okay? And secondly, that the largest of these things that's involved is as small as possible. Right? This 536 means that you have 1 over 536. If you're dividing a pie or a loaf of bread, you have to divide it into 536 pieces. So that's a lot of work, okay? So you want this kind of number to be rare. And you want to minimize the biggest number that appears here. And modern computer studies of this problem basically confirm that, I think probably without exception, that Ames gets it completely right. And it's a highly non-trivial task. And we don't actually really know, I think, how systematically he exactly did this. Or maybe he was just copying something that's already, several hundreds of years old already. All right, so for completeness, here's the rest of the table, 75, 77, up to 87, and then to 101. So here are all of the entries on Ame's table found in the Rhind Papyrus. And if you're a student of mathematics, it's well worth sort of pondering these things and sort of playing around with them and appreciating the sort of serious arithmetical competence that is represented by this information. Let me give you an example of how this could have been used. So we were talking about 5/7 before. So how might Ames have found this particular representation of it? So this is an illustration of how this sort of doubling aspect also appears. So 5/7 can be written as 1/7 plus 4/7. And we write the 4/7 as 2 times 2/7. So again, we're using this binary kind of orientation that the Egyptians had. Okay. Now the 2/7, that we look up on the table. Okay, if you look on the table with a 7 here, there's a 4 and a 28 in the unit fraction column. That means that 2/7 is equal to 1/4 plus 1/28. That's what we've looked up. Okay, so now we expand this. Well, there's a 1/7. 2 times 1/4, that's 1/2. 2 times 1/28, that's 1/14. And that's how we get, then you rearrange them so that the biggest one is at the beginning. So you get 1/2 plus 1/7 plus 1/14. That's how this kind of arithmetic would have been used. So that you can sort of, with a bit of skill, you can reduce everything to knowing how to express these ratios to over an odd number in terms of Egyptian fractions. So let me give you one more example of how Ames' table could be used. Suppose we want to understand what we would call 8/93. Maybe you have 8 barrels of beer and you have 93 workers and you have to divide them. Okay, so we write 8/93 as 4 times 2/93. So now this 2/93 is something that we can look up on our table. And on the 93 row, there's a 62 and there's a 186, telling us that 2/93 is the same as 1/62 plus 1/86. Okay, so then we can do a little bit of cancellation, sort of divide by 2's, so that becomes a 2, and here there's a 1/31 and a 93. And now we have 2/31 plus 2/93, and now we have some more lookups that we can do. Right? We look on the row that has a 31, we see that 2/31 is the same as this, 1/20 plus 1/124 plus 1/155. While 2/93, well, it's the same thing we already have. That's 1/62 plus 1/86. And then we put them all together in sort of increasing order. 1/20, 1/62, 1/124, 1/155, plus 1/86. Okay, so this is maybe not the most efficient expression. In fact, there's other ways of expressing this. In fact, here's a much simpler way. This is obtained by what's called the greedy algorithm, which arguably perhaps goes back to Fibonacci. So a way of this greedy algorithm, what you do is you divide 93 by 8. Okay, you divide 93 by 8, it goes 11 times, and then some remainder. So that means if you take the number next bigger than 11, that's just 12, that you can peel off 1/12 from here, right? So this is kind of like the biggest fraction that you can, of the Egyptian kind, that you can peel off from 8/93 and still get something that's positive. So if you do that, you take the difference between 8/93 and 1/12, then happily in this case, it becomes just an immediate Egyptian fraction. So that's kind of a stroke of good luck. You just get 1/372. So arguably this is a simpler result, but perhaps if you were actually subdividing things, you could argue, well, yeah, but this has a 372, and here the biggest one is over 186. But it does bring us to an interesting point that the greedy algorithm, you can also apply that to Ames' table, okay? And you can compare the results of the greedy algorithm, which gives you just a clear-cut answer for each one of these things. And it turns out that Ames' table is obviously superior to what you can get with the greedy algorithm. Okay, so if you just do the simple kind of minded thing that you might do if this was a computer science programming class, you would not get as good a result, as a practically useful result as that found on Ames' table. So I hope that gives you some sense of a couple of things. First of all, an appreciation for Egyptian arithmetic. Okay, it's not just a recreational device. Often these Egyptian fractions are thought of as, it's a kind of cute little thing that, it's recreational mathematics. But no, it's actually a legitimate point of view towards using fractions. And if we actually had to do arithmetic in our real world and we could not use decimals for some reason and we had to use fractions, I think it would be a very interesting question. to say, well, should we go with our current system of fractions, or should we adopt something like an Egyptian fraction point of view? Probably a case could be made that the Egyptian fraction point of view has some advantages over our system. That's pretty interesting. In our next video, we're going to be looking on the other side of the Red Sea, in the Mesopotamian region, the Babylonian Sumerian tradition of arithmetic, which is just as interesting and fascinating as the Egyptian, and also sheds light on our arithmetic too. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.